Hello, thank you so much for tuning into my YouTube channel. In today's video, I want to talk about how we can see colors. This is a very complex topic, but I'm just gonna cover the basics of it and see how we are able to see colors like red, green, and etc. Let's get started. As I said in this video, I want to talk about how we can see color. We're gonna talk about how light is detected and interpreted through our visual system and results in the stimulus having a particular color. The conversion from light energy to color names such as red, green, and blue is exceedingly complex. Fortunately, it is not essential for the purpose of this video to know in detail how the visual system works, and knowledge of a few basic principles suffices. Light entering our eyes is imaged onto the back of the eyeball, the retina, where light receptors absorb a portion of the incident light and generate a signal eventually interpreted by the brain. The quality of the retinal image depends on the absorption, scattering, and focusing properties of the cornea, lens, and fluid filling the eyeball, aqueous and vitreous humor. There are two classes of receptors, rods and cones, named according to their shapes. Rods detect very small amounts of light, such as starlight. Because there is only one pigment type, we only see objects as shades of gray. As the amount of light increases, the rods become desensitized and cease sending signals to the brain. During the day or in a well-lit room, the rod signals are inactive. Cones, the second class of receptors, have much lower sensitivity to incident light. As the amount of light increases, the cones start sending neural signals. The cones are our color receptors. As the sun begins to rise in the morning, the gray world becomes colored. Our sensations of color are a result of having three types of cones responding differently to light of various wavelengths. Stimuli that cause different colors have different cone signals. The letters L, M, and S are used to represent the three cones with their peak sensitivities in the long, middle, and short wavelength regions, respectively. As shown here, their spectral sensitivities overlap quite a bit, particularly those of the L and M cones. This improves color discrimination. If the receptors did not have any overlap in their spectral sensitivities, we would only perceive three hues in the spectrum. When two stimuli, whether colored lights or illuminated materials, produce the same cone signals, the two stimuli match in color. The cones, as do any other detectors of radiation, integrate the light at all wavelengths incident on them. Each such integration of all the incident wavelengths reduces the entire spectrum of incident light to three signals, one for each type of cones, resulting in what is called trichromacy. Trichromacy leads to perhaps the most important property of the visual system, called metamerism. Stimuli do not have to have the identical spectral properties in order to match in color. It is possible to match colors without matching the physical properties. There are many examples of metamerism in our colored world. The displays could produce a wide range of colors that match many objects. Because of metamerism, color reproduction is possible. The rods and cones in the eye form a retinal mosaic. The detectors are closely packed as in a mosaic, with the pattern varying in its arrangement throughout the retina. In the center of the eye, or fovea, only cones are present. Foveal vision is used for distinguishing very fine details, such as reading or seeing objects at a distance. A yellowish pigment, the macular pigment, is also present on the fovea. The macular pigment helps protect the foveal receptors from damage from sun. Outside the fovea, the number of cones is greatly reduced, and they are situated quite apart from one another. The remainder of the mosaic consists of rods. Each individual receptor does not have a separate connection to the brain. Rather, receptors interconnect within the retina, forming receptive fields. It is interesting to note that resolution, the ability to resolve fine details, depends ultimately on both the spatial mosaic of the receptors and how they interconnect. There are far more L and M cones than S cones. Because the optics of eye have inherent limitations, short wavelength light is quite blurry by the time it reaches the retina. Therefore, having increased number of S cones is unnecessary. In forming receptive fields, the individual cone signals can either add together or be subtracted from one another. Because the L, M, and S cones have different spectral sensitivities, different numbers, and different mosaic, the receptive fields have quite different properties. As a simplification, we assume there are three types of color receptive fields, called opponent channels. The black-white or luminous channel results from the addition of L, M, and S cones. It has the highest spatial resolution, as shown on the left side. The red-green channel is mainly a result of the M cones being subtracted from the sum of L and S cones. Its spatial resolution is slightly lower than that of luminous channel. The yellow-blue channel results from the addition of L and M and subtraction of S cone signals. It has the lowest spatial resolution. You can also see the sensitivities that are both negative and positive, which results from the interaction of the three cone receptors forming opponent signals. You could also see the sensitivities that are both negative and positive, which results from interaction of the three cone receptors forming opponent signals, as shown here. The concept of opponent channels was first postulated by Herring. Soon after that, vision scientists started arguing whether visual system was trichromatic or opponent in nature. But now we know that both occur in stages, called stage theory. So first, the photoreceptors absorb the light and then they get combined, leading to opponent channels. The opponent signals leave the retina via the optic nerve and eventually arrive at the back of the brain. The brain signals are interpreted through a cognitive process that results in color. So the opponent signals leave the retina, they go to the back of the brain here, called primary visual cortex, and here the color is interpreted. There are so many other factors that affect what a color of an object seems to be, such as observer's adaptation level, the environment that the object is in, the immediate surrounding of the object, and so on, which we cover in the later videos. This video showed the basics of how we see color. Thank you so much for watching this video. I hope you liked it and you were able to get something out of it. If you liked it, I would appreciate if you subscribe to my channel and even share the video with your friends. Thank you and have a nice day.